My name is Joshua Lind, and today I'm going to be presenting Teechain, which is our secure and scalable Layer 2 payment network. So before we dive in, a quick summary about myself. I'm a PhD researcher at Imperial College in London. Currently work in the large-scale data and systems group, and the research that I do focuses on the security, privacy, and performance of distributed systems. Very vague, I know, but it's anything from cloud computing environments to peer-to-peer networks and blockchains. So, I know we've just had lunch, and some of you might be tired, so if you don't want to listen to anything I have to say today, just look at this slide, take a picture of it, and you should be good. So Teechain is a Layer 2 payment network. It's currently about 150 times faster than the existing implementations of LN that we've compared it to. It places anywhere between 20 to 80% less data on the underlying blockchain. This is obviously subject to some constraints and assumptions that you make. It reduces the collateral fund lock-in, i.e. the amount of funds you need to lock into the network in order to tolerate peaks and changes in demand. And it gets its security from three aspects. Each of these I'll explain in a bit, but they're essentially the use of trusted hardware, chain replication for fault tolerance, and what we term asynchronous blockchain access. So for anyone who's interested, we have an alpha release for Bitcoin, which can be found at teechain.network. So I won't bore people with the background. Essentially, we know blockchains aren't really scaling. And the question that people often ask is, can they kind of handle the workloads that we see in the real world today? Of course, the answer is yes. Point-to-point payment channels, off-chain scaling, typically operate in three phases. Setup phase, you put some money on the blockchain, executes payments very, very quickly off-chain, and at some point, one of the parties wants to settle the channel. Of course, as we've heard already this morning, what makes this difficult is the need to revoke old payment channel states. If you get this wrong, people can, of course, spend and can steal funds. So, what is the problem that we're trying to solve? Well, existing solutions assume synchronous blockchain access. They create transactions with time locks, and they assume that such transactions can be placed into the blockchain within a given amount of time. So for example, in LN, you monitor the blockchain, somebody does something bad, you have a certain amount of time to react. The problem with this is that blockchains provide no formal write latency bounds, right? So earlier this year in February, we saw a spike in the confirmation time for Bitcoin transactions, spiking from about 2 hours to 2 days. And this was due to network congestion. And the problem is because we have no formal guarantees here, an attacker can exploit these kinds of latency problems by breaking the assumptions of your payment channel. Now, there's various different ways to do it. Network congestion is also one, but you could also have transaction censorship through miners. We've seen a little bit of this happen in Ethereum already. So that was the first issue. The second issue is that existing solutions typically face long channel creation times, right? In order to create a payment channel, I need to place a transaction on the blockchain. In Bitcoin, that takes about an hour. So we want to sort of avoid this. Ideally, if I want to make a payment to you right now, I don't want to have to wait. And finally, we want to reduce the amount of collateral fund lock-in, right? So it would be nice if we could have funds in the network and dynamically assign them to different payment channels as we need. Now, of course, there are some works which take some steps to addressing this. For example, channel factories. I think Christian's here somewhere. But they're, first of all, they're sort of specified to a subset within the network, and they require that subset to participate. In Teechain, we want to avoid that. We want to be able to put funds in the network and put them anywhere and take them out of anywhere dynamically. So here's a quick summary of the existing solutions in the space. Of course, not all of them, but essentially, they all suffer from these same problems. And this brings us to Teechain. So the idea of Teechain is to effectively address all of these. And the way that it does so is that it revokes old payment channel states through the use of trusted hardware. I know what you're thinking, Spectre, Meltdown, it's all broken, why are we wasting our time? But suspend your disbelief, we'll get to that in a bit. But trusted hardware, as we've already heard about this morning, is currently happening. When I say trusted hardware here, I of course mean trusted execution environments. We've heard a little bit about this morning, so I won't bore you with the background. But essentially, you get confidentiality and integrity guarantees for code. Various different hardware vendors in the space. Intel SGX is, of course, the main player at the moment. It allows you to create enclaves, which effectively protect you from software-level attacks, such as higher privileged software, your operating system, your BIOS, but also protects you from hardware attacks. So assuming someone has access to the machine, assuming that they never can physically breach your CPU package, your data and your code should be safe. I say should be, but let's discuss that in a bit. The way that this is actually realized is effectively your enclave code and data is stored in the enclave page cache, which is an on-chip cache. And effectively, any time that it's brought off of the chip to, for example, when it's flushed to RAM or disk, it's encrypted and integrity protected by the memory encryption engine. And any time it's brought back on, it is verified and decrypted. And the final aspect that we have with trusted execution is that what we can do is we can create what we call hardware roots of trust. Effectively, you can create some form of trusted notion in an untrusted environment. The way that this works is typically what you'll do is perform a hash over your enclave code and data, sign it using a key that's physically burnt into the CPU. This gives you a measurement, which tells you two things. One, the exact code and data that was loaded into the enclave, and two, whether or not the enclave is genuine trusted hardware. So, Teechain uses trusted execution environments to create secure payment channels. Each user has their own trusted execution environment, typically. And these store deposits, authorize payments, and generate transactions in the blockchain payment network. Now, we face three challenges when designing Teechain. The first is, of course, the need to operate with asynchronous blockchain access. We don't want to assume read or write latency bounds to the blockchain. Next, we want to support efficient deposit assignment. So we want to be able to add and remove funds to payment channels dynamically and create payment channels really, really quickly. And finally, we need fault tolerance. So we don't want funds to be lost if one of our devices dies. So here is a brief summary of the Teechain network. There's a lot going on, but I'll explain it. Essentially, it's made up of users, payment channels between users in the form of edges here in this graph. You can have payment chains, which are essentially just multi-hop payments in LN. So Alice can send to Bob through some payment processor. Users without trust and execution environments can still participate in Teechain. The way that they can do this is what we call through channel outsourcing, which I'll explain later on. And finally, you can create backup chains, which are effectively replicated enclaves to store state or replicated trusted execution environments. And so this is one way to protect yourself against a failure. So let's take a bit of a deep dive and see how Teechain operates. So we have a user here, Alice, with her own trusted execution environment and a connection to the blockchain. Now, if Alice wants to deposit funds into Teechain to begin making payments, she essentially creates deposits, which are basically just payments to an address which is owned exclusively by her trusted enclave. Now, what she'll do is forward those deposits onto the blockchain, and she'll notify her TE of that. If she wants to create a secure payment channel between herself and Bob, the first thing that needs to happen is we need to create a secure communication channel between the two enclaves. Essentially, this is just done by generating a secure public-private key inside the enclave, performing a remote mutual attestation, and authenticated Diffie-Hellman. So after this process, you have a secure communication channel between Alice and Bob. Alice's enclave and Bob's enclave. So note here that Alice and Bob can't really interfere with messages. They could drop or replay messages, but they can't read or write them. And using this secure channel, you can basically instantiate payment channels between the two users very, very quickly. So, Alice wants to pay Bob. What she needs to do is associate one of her deposits with the channel. She does this by effectively contacting her enclave, saying, hey, I'd like to deposit some money into this channel with Bob. Her enclave notifies Bob's enclave of the incoming deposit. Bob verifies that the deposit is indeed on the blockchain, so however many confirmations that he requires to see. If he's happy with it, he notifies his enclave, which tells Alice, hey, we're happy for you to put the money in the channel, and Alice's balance is pretty much just updated by the deposit. Alice can now pay Bob. Very, very simple, construct payment messages. She talks to her enclave, which updates her balance, forwards it to Bob. And so both of the balances are updated either side. Note that on channel creation, so on deposit association here, I've just skipped over this. When you add a deposit to a channel, when you associate it, the private key, in order to spend that deposit, must be shared with a counterparty. This is because Bob doesn't want to trust Alice for availability in order for him to terminate the channel. If he wants to terminate now, he shouldn't have to say to Alice, hey, I want to terminate the channel. And Alice says, well, actually, you know what, you can't. So what we do is we effectively outsource the control of these private keys to the trusted enclave devices. I'll come back to this in a bit. So now, payments can be issued. Bob can also pay Alice back. Should Bob want to add funds dynamically to the payment channel, he can do exactly what Alice has done in the past, create a new deposit on the blockchain associated with his channel. Private keys are shared, and now his balance has been updated. The cool thing about this is that if Alice's balance allows, let's imagine Alice has another payment channel which is receiving high peaks in usage, and she needs to add more collateral to this. What she can do is actually dissociate the deposit from this channel, which is very similar to association. Effectively, she notifies her enclave to say, hey, I want to remove this deposit out of the channel. Assuming her balance is correct and allows her to do this, the two enclaves will effectively update the payment state, and this deposit now, A2, is ready to be used in another payment channel. And finally, at any point, each of the users can settle the channel. So let's say Bob wants to settle the payment channel. He contacts his enclave here, generates a single settlement transaction, which can then be forwarded to the blockchain. So note that we don't have this issue of revocation, right? There's only one transaction being generated, and that's for the final state of the payment channel. So we've seen how payment channels work between Alice and Bob. Of course, Teechain supports multi-hop payments. So let's say Alice wants to send a payment to Carol through Bob. The way that this is done intuitively is effectively you want to construct a message which sort of propagates down the chain and updates all of the balances. So that at the end, Alice and Carol, Alice has now got a balance of 0, Carol now has a balance of 5, and all of the balances are updated atomically along the chain. With this, you need to ensure that all channels update atomically, right? If only some of the channels update and some don't, you can lose funds. So how does Teechain achieve this? Well, it offers a payment chain protocol, which we've designed. It updates all channels atomically, so either all channels process the payment or they don't. During this time, there's no need to monitor the blockchain, as with LN. And finally, during this time, you can also actually allow users to settle their individual payment channels. So let's say a payment's being routed through the network, and Alice decides, actually, you know what, I want to get my money out. She doesn't want to have to wait for this payment to complete. Let's say somebody's taking their time. So what she can do is she can actually settle her individual payment channels and prematurely terminate the protocol. Now, this might seem counterintuitive to a few of you who've sort of looked into how this stuff works, but one way to attack this, let's say that Alice is paying Carol. So imagine that Alice constructs a message, says, hey, Carol, I'm paying you $5, forwards it to Bob. Bob updates the channel state with Alice. But before he can send the message to Carol, she decides to settle the payment channel. So of course, we have a problem here, right? Because you've got two channels in different states. Post-payment state, pre-payment state. So what Teechain does to avoid this is it effectively uses what we call proofs of premature termination. The idea being that for any channel C1 in a state X, its settlement transaction will conflict with any other channel, a C2 in a state Y, where the two states are different. So let me give you an example here. So here we have the two channels in the chain with different states. Should the two users decide to settle their payment channel in the different states, these two transactions conflict, right? Only one of them will be placed in the blockchain, in this case Alice's. And what Carol can do is then go to the blockchain, use that transaction, and present it as a proof to her enclave that Alice prematurely terminated. It's quite simple. Her enclave will then generate a non-conflicting transaction at the same state, X. So here the whole point of this is effectively to ensure atomicity of all the channels. So here is our payment chain protocol. I won't go through each of the 6 phases, but essentially it's sort of similar to a 3-phase commit with channel locking on either side. And the proofs of premature termination are used between state transitions 3 and 4 and 4 and 5, i.e. when you're updating balances. So how does asynchronous blockchain access work in Teechain? Well, Teechain only requires access to the blockchain in 2 cases. 1, when you're synchronizing deposits, and 2, when you're generating settlement transactions to close payment channels. So you can think about this conceptually that imagine Alice and Bob synchronize deposits with the blockchain. They understand, they have some view of the blockchain. Then they get shipped off to an island somewhere, and they can only communicate with each other. Here they can still set up channels, associate deposits, make payments. They only need to settle the payment channel by contacting the blockchain and coming back to the mainland. So, the astute among you will notice that enclaves or trusted hardware devices store private keys. What if these things die? Do we lose money? Well, no. Teechain provides 2 options for fault tolerance. The first is persistent storage, The second is chain replication. The idea here is that upon a failure, users can still settle their payment channels and get their money out. So how does persistent storage work? It's actually quite simple. On every channel state update, you effectively write the new state to your hard drive. Should your enclave die, you then reload the state back into the enclave to settle your payment channel. This obviously requires the use of hardware monotonic counters to prevent replay attacks. The problem with hardware monotonic counters, at least at present, is that in Intel SGX, they're rate limited to about 10 operations per second. You can sort of get around this in payment channels by batching transactions at the client. So you're not forced to only have 10 transactions a second in your payment channel if you're using this. You can obviously batch at the client multiple transactions into one while you wait for these operations to occur. But we want to avoid this entirely. So another option is, of course, chain replication. So chain replication offers strong consistency and high availability. The idea is effectively you replicate your state of your primary TEE to a set of backups. Any state updates for your channels will propagate down the chain. All of the nodes are therefore synchronized, so somebody can't double spend funds. Failures along the chain will break the chain, which means your payment channel states can no longer be updated. And so what Alice will have to do is contact one of the enclaves, the one that's still alive, to settle her payment channel states. So using chain replication, we can allow people who don't have access to trusted hardware to participate in Teechain. And the way that we do this is through channel outsourcing. The high-level idea is actually quite simple. You select a set of enclaves in the network that you're willing to trust. You construct a backup chain along that set of remote TEEs. And the idea here is that you're not actually trusting the operators of these TEEs with your money. You're trusting the hardware devices themselves. You're just making the assumption that at any point of time, at least one of these people will be online for you to get access to your funds. So we implemented Teechain. I'll present some performance results here. We created a payment channel between Imperial College and Cornell on the Bitcoin mainnet, well, several payment channels actually. In the case of Teechain, we put backup replicas in Israel. Here are some of the results. So in the case of the Lightning Network, we used the LND implementation from the Lightning Labs. We achieved about 1,000 transactions a second, give or take, with a latency of about half a second. In the case of Teechain, however, we're able to achieve about 135 to 145,000 transactions a second, with similar sort of latencies. In terms of channel creation, of course, with the Lightning Network, you require 60 minutes because you're forced to push a transaction down to the blockchain. With Teechain, however, you can create a payment channel in about 2.8 seconds, and you can add funds to those channels in about half a second. So within 3 to 4 seconds, you're pretty much good to go. We also evaluated payment chain performance. The idea here is that we basically varied the number of hops in a payment chain. We execute payments, measure how long they take to process. In both Lightning Network and Teechain, of course, latencies increase linearly, which makes sense. The more nodes you have in your chain, the longer it takes messages to propagate. What's interesting here actually is that the Lightning Network has a lower latency for payment chains. And this basically just comes down to the fact that they assume synchronous blockchain access, right? You have to be monitoring the blockchain while executing these payments. In Teechain, we make no such assumption. So we're forced to basically send additional messages along the network, which require longer latencies. But in terms of throughput, Teechain is anywhere between 60 to 25 times higher throughput for payment chains of length 2 to 11, or number of hops, sorry. And this basically just comes down to the fact that Teechain is more efficient at batching transactions. We also measured the on-chain channel cost. I won't go too much into the numbers here, but feel free to ask me afterwards. Essentially, Teechain places anywhere between 20 to 80% less transactions on the blockchain. It's even more in the case of unilateral dispute, where two parties disagree. Of course, we've made some assumptions about channel factories, but yeah, we can discuss this offline about what sort of assumptions we made there with those variables. So I know I don't have a lot of time left, but what I will do is talk a little bit about the security of Teechain. So the first point that I want to make is that we've proven the correctness. When I say correctness, I mean balanced correctness of Teechain using the universal composability framework. And the idea here is that balanced correctness basically just says that at any point in time, a user can get access to their funds on the underlying blockchain and have the correct amount of funds corresponding to the payments that were actually executed. I.e., regardless of what anybody else does, your funds can still be settled down to the underlying blockchain and you won't have lost any money. So, what about hardware attacks? Well, there's 2 points to make here. The first is that in Teechain, we mitigate side channel attacks, specifically timing and memory access-based side channel attacks. The way that we do this is what we do is we isolate the private keys inside the enclave from the rest of the code and data. We use trusted side channel resistant libraries on those private keys. And the way that we ensure that only those libraries are accessing those private keys with direct invocations is through the use of static analysis. So specifically forward and backward slicing. I'm happy to discuss that afterwards as well. But the second point to make here, which is perhaps a little bit more interesting, is, well, what if I don't trust Intel, right? You know, we're always hearing about Spectre and Meltdown, and every week somebody's breaking a branch predictor or, you know, some segmentation in Intel processors. Well, first of all, Teechain is not specific to Intel SGX. We require a trusted hardware vendor who supports remote attestation, right? Ideally, we want to see many, many different hardware vendors in this space, and I think people are moving towards this. Sure, it's not ideal at the moment, but I think it basically brings up a more fundamental question. And I'm willing to argue a little bit that I think already we're making implicit assumptions in trust with current processes today, right? Intel, AMD are giving you these black boxes. We're assuming that they implement speculative execution correctly. They don't. And so you have all sorts of attacks being found. And essentially, one thing that we're trying to question, and we would like to see what the community thinks about this, is whether or not open source hardware should actually be brought to the real light. Because I think at the moment, there are implicit trust assumptions everywhere. And finally, in Teechain, our trust model is channel-bound. So it doesn't affect the underlying blockchain, and it doesn't affect any other payment channels in the network. So if you're willing to trust Intel, and I'm willing to trust AMD, we can still create a payment channel between us, and we should be happy. Another way to mitigate these sort of attacks is you can also bound your losses, right? You can say, well, I'm going to use Teechain for $20. I'm going to get really, really high performance. I can put my $20 anywhere. Sort of similar to the gift card idea Pedro talked about this morning, but rather than gift card, it's actually cash, right? Because I can put it in any different payment channel that I want. So there's a bunch of future work we can go into. I won't for time reasons, but privacy, performance, practicality, cross-chain swaps is one example. What about actual scalability? So this is some questions that haven't actually been answered, at least in my opinion, in the payment channel network space already. How do these things actually scale? What are the latencies? What are we actually seeing with throughput? So I want to thank you very much for listening. Hopefully I haven't bored you too much. If you have any questions, I think now is the time.
Awesome. Awesome, awesome. Okay, so is there any questions? Yep, down the back here.
If you talk about trusted computer, trusted hardware, do you mean it in the way of trusted platform module?
So trusted platform module is one way to
what you mean with this actually, or do you have a different concept behind?
Well, so from what I understand, trusted platform modules don't necessarily in all cases provide remote attestation, right? Intel SGX does. It sort of gives you the confidentiality and integrity guarantees with remote attestation. And you need both of these things in order to operate. So whatever trusted hardware you're talking about, if it can provide both of these things to me, under the cases of hardware level attacks, then we're good.
One more question to these, actually connected. We have checked with a few students in their private laptops how much they use trusted platform modules, and there was from 10 laptops only one containing this security element, remark number one. And my question is, do you have plans or are there implementations for your protocol on the basis of other hardware modules, especially of smart cards, namely Java cards?
So to answer the first question regarding the availability of this stuff, so my understanding is that Intel SGX is available in any laptop bought since 2015. It's part of the Intel Skylake architecture. They also have servers and stuff coming out. There's already 4 cores and I think now 8 cores available. Regarding the smart cards idea, this is something that we've speculated about, but we haven't actually talked to anybody directly about implementing this. Brilliant.
Hi, thank you for your talk. I had a question about the monotonic counters. Can you explain a bit better how like having potentially broken monotonic counter would affect the viability of the application? Because I remember a paper from 1 year ago, which was showing how those monotonic counters, which basically provide statefulness, they are not within the trusted boundaries. And in some cases, removing the BIOS battery, you reset them or things like this. So.
No, sure, exactly. So from what I understand, the hardware monotonic counters, and Intel hasn't really released a statement about this, but from what a lot of people speculate online, it's currently implemented within they have this remote execution engine, right? It's not actually part of the Intel SGX on the chip. In terms of the breakages, yes, you can remove this engine and effectively write over the state of the hardware monotonic counter, but from what I understand, you can't write back to a previous state. You can completely kill it, which means you can't roll back to anything at all. It's either state X or state 0, but you can't go to state X minus 1. This is my current understanding.
Also, maybe I have one more question over here as well.
I think my question goes in the same direction. You talked at length about the clonability of the backups and stuff, and I'm wondering what prevents you from having a Sybil attack in those perspectives. In a Byzantine way.
Okay, so you're asking specifically about the chain replication, is that correct, with fault tolerance? So because we're using Intel SGX, we don't have Byzantine failures. We have crash failures, right? We know what code's running, and so our nodes can't sort of misbehave. Either they die completely, or they execute the protocol that we tell them to execute. Well, I mean, this is the guarantees that trusted hardware gives you, right? It gives you confidentiality and integrity. You load it. It's like a smart contract with confidentiality. You give it code, and either it executes the code or it doesn't, right? Someone can pull the power out of the machine. Great, it's gone. But so we don't have Byzantine failures in our model. We basically have crash failures, and this is why what we need to do is effectively just update the states of all of the nodes and sort of not worry about any of them misbehaving. They could die, but that's why we have fault tolerance.
Awesome. Thank you very much. So, a round of applause, everyone. Yes? Okay.